without dealing it further, now I would like to call our guest speaker to carry forward with the session.
Hi, good morning. Yeah, first, how many of you interested in EV? For EV? Around 60%. Good. Okay. Next question. In EV, what area you are interested? What area? Powertrain. Okay. No energy system. No. Okay, fine. So, okay, let us understand what is EV in this one, and what are the major areas, and what are the major challenges, and where employment opportunities are available today. Okay, so let us understand that one. And okay, so yeah, good one. Not to feel nervous. Yes, the failure is part of life.
Yes,
so when you fail, then only will succeed. Okay, that is good. Okay, then. So.
Yes, from up. Yes, you have to press and it will change.
Yeah.
So I think
yeah, it has been. Okay. Fine. So yeah. So let us start. Okay, and this is a brief session. Okay, in this one, what I do is that I will take you through what is EV architecture. Okay, and what are the EV constituents rather? Okay, subsystems, and then briefly touch upon okay, the challenges what we are having today, and also I tell you where the employment opportunities are available. Okay, so sometimes that is critical one. Okay, so in academic institutes, no problem, because based on my area of specialization we work, but long term that is also thinking. So EV wise, okay, it is not a new one, nothing new. Okay, now it has become a new area because everyone we are saying that it is new. But if you historically, you people know that, you must have already studied. You may be having that basic background more than me rather now. That this is nothing new. This is the old technology. Okay, this technology was available in the 1800 itself, before the IC engines came into the market. Before the IC engine, whatever we see, all IC engines, okay, internal combustion engines, before them, the EVs were there. It was in 1800. Okay, so there were more electric vehicles than the EVs. Okay. Okay. So yeah, fine, no problem. So okay, this is just a historical perspective. In 1900, there were okay, less than 1,000 IC vehicles, but more than nearly 1,600. It has gone back. Huh?
It is.
Yeah. Yeah, that's why we call it educational institute. Educational institute is another word. It will be all failures will be continuous. But okay, so no problem. So hey, why it is going so many things? Now it will be fine. Many slides. Okay, fine. Okay, no problem. Okay, and what I am saying is that nearly 1.5 times more okay, EV vehicles were there. So these people were preferring these things. These vehicles.
You can come here only, sir. We can upload.
Hello. Yeah, people were preferring these vehicles, okay, because they were less noisy. And initially, when ICE vehicles came, ICE engine vehicles in our generation, when they came, starting was the trouble. We have to okay start the vehicle. They are not self-starting vehicles, ICE vehicle. Now we are putting a battery and starting. So starting was a trouble. And because EV vehicles were self-starting vehicles, and also gasoline vehicles used to create a lot of smell as well. Okay, so smell not clean and so many things were there. That's why people were liking. And they were in the, very useful in taxis as well. And whatever we call today the swapping battery. So still India is struggling with swappable battery policies. Those policies were already there at that time. You can see the last slide where, last one, wherein the batteries are replaced, charged batteries are replaced here. Okay, move to the next one. Okay, this is only historical perspective. Next slide. Okay, yeah. So if you see this slide carefully, okay, this is an interesting slide. Okay, this is a 1965 vehicle. Okay, very, very well established vehicle. You can wish you can sit there. Okay. And otherwise we will be starting off. Okay. Yeah, we can. उसमें a lot of disturbance is coming from that. So एक time So in this slide, what it shows is that in 1965, this car is highly matured car, but in this one, there was not a single processor. There was not a single microcontroller or a processor. In automotive world, we call them microcontroller. There was not a single microcontroller in this one. Okay, so no control. Everything is managed mechanically. Okay, go to the next one. So if you see today's vehicle, so left side is the old vehicle wherein everything is mechanical. Okay, either mechanical, pneumatical, or hydraulic controlled. Okay, nothing electronically controlled. If you see the right side one, nothing is today mechanical. Everything is electronically controlled. You see your power steering, it is you have seen your power steering you are having. Windows control is this one. Even your tire pressure monitoring is also electronically controlled. Everything is electronically controlled. Nothing is mechanically controlled today. So paradigm shift has happened from mechanical controls to the electronic control. And electronic control requires a lot of software. So there is a shift happened. Okay, so in the all advanced vehicles, you see lot of electronics and software. Go to the next one. Okay, so what we are seeing today is that 70 to 90% of innovations in automotive, okay, in general automotive I'm talking, is happening in the embedded electronics and controls. 70 to 90%. Okay, so in that one, the nearly 30 to 40% of the vehicle cost is coming from the electronics and software. Okay, so mechanical systems have matured. The technology has so much matured. It has matured. Technology is matured. Now, whatever the new things are coming, where the costs are going, they are going in software and electronics. So the other one in the automotive industry today, you go to any automotive industry. So 50 to 70% of the investments, whatever the R&D investments, are going in the software and firmware and electronics. Okay? In the automotive industry, I'm talking. Okay? Yeah. So now you know that EV is making a lot of buzz, particularly in India, and globally it is making. In China, it is started dominating and other things. Why it is so? Okay. If you see this slide, the basic difference it is providing. So you know that the ICE engine maximum best efficiency you can get is around 20, okay, not more than 20 to 24%. Okay, around 20% only at the wheel. You can see the top one. Okay, and whereas the EV, even if you the worst case scenario, you will get around 80% efficiency. Okay, so then immediately you may ask, very simple, that if such a nice and it is a 4 times higher efficiency, then why EV is still struggling to come in the market. Okay, so efficiency wise it is good. Only the problem is the availability of the fuel. Okay, so fuel is nothing but in EVs it is battery. Battery cost is higher compared to the cost of the fuel for the IC engine vehicles. Okay, but that is drastically reducing. Those things we are touching up in this talk. Okay, next. So let us understand the EV architecture. Okay. Okay. Now this is a fairly simple thing here, and I'll be asking now that first one. Okay, first left one. Okay, last bench. Okay, can you tell me what is the architecture of the first left? First left. IC engine. Very good. Okay. So fairly simple. Okay. Next is a parallel hybrid. What is a parallel hybrid? Parallel hybrid is nothing but in the IC engine, the powertrain or a drivetrain is driven by an ICE engine, internal combustion engine. In a parallel hybrid, there will be two powertrains, two drivetrains. Okay, so and independent, it can work independently with the ICE, it can work independently with the electric motor, or it can work with both. So that is nothing but you are having a two high power drivetrains available in a vehicle. This is possible in a larger vehicles. Smaller vehicles, so much space is not available, so much cost also one will not put. So there will be in the larger trucks and other things, they will put that one. So you may be knowing the advantages of EV and advantages of ICE. Okay. Consider in a highway run, okay, which is more efficient, EV or ICE vehicles. Consider in a Noida kind of a city with so much traffic and other things, which vehicle is EV. So now you know that higher. Okay, if you take the gears, okay, more than 3, 4, 5 gears, your ICE vehicle is more efficient. In a second, first gear, lower speeds, EV is more efficient. So in a parallel hybrid, this can be utilized properly. So you can, when you are running in highway, use the ICE vehicle, and when you are running in a city, use the EV powertrain. So you can get the best of the both worlds. Okay. Next is a plug-in hybrid. Don't go to plug-in hybrid. First, I will close this one. Start-stop. Start-stop is nothing but it is an ICE vehicle. Okay, only it will be having it is having a provision to stop the engine whenever it is not needed. It will be having a larger auxiliary battery to restart it. Okay, that's all. Okay, so it is that is a start-stop. Then comes the series hybrid. In series hybrid, the fuel, okay, input is only the basically it is a prime mover is the electric. Okay, prime mover is electric, and there will be sorry. In a series hybrid, the prime mover is electric, but there will be both the powertrains available, motor as well as the ICE. But the ICE is not driving directly the vehicle. It has to drive the motor. Okay. So there is other differences there. Just you can have a close look in the series hybrid. The fuel is basically fuel is here, whatever the diesel or petrol is the fuel, and it will charge the battery. Once you run this one, it can drive the vehicle or it will charge the battery as well. Okay. So basically there is power to the battery is coming from the fuel, whatever petrol or diesel. In a plug-in hybrid, difference is that battery can be charged externally. That is the only difference. In a series hybrid, the batteries are charged only through the running the engine. In a plug-in hybrid, battery can be charged through externally by connecting to the grid power. And the next one is a battery electric vehicle. So there is no ice at all there. Okay. So hope these architectures are clear. Okay. So they're fairly simple architectures. No. Okay. Fine. Next. Yeah, this is a EV architecture. Okay. So those who are from EV background, now you must be knowing all these things, fairly simple. So major one is the battery, which is the fuel, okay, which is replacing the fuel tank of an ICE vehicle. Okay. Then there is the ICE, in ICE vehicle, engine is replaced by the motor. And the motor, nowadays, the engines are also having their engine controls, ECUs and other things that you can consider as a motor controller that is controlling the motor. Okay. And further is the transmission. Transmission is there in ICE vehicles. There are multiple ratios there. Okay. Up to 5 ratio, we are having the transmission is ultimate gearbox. So you are having a 5 ratio there. But in EVs doesn't need that one because EV is having a variable speed drive, VFD. So once you are using a variable speed, you can control the speed. So that's why it is normally single ratio transmission or a dual ratio transmission which will be there. That is the gearbox. Then the next one is important one is the charger because the batteries requires charging. So you can have an onboard charger. Onboard charger, there is a limitation. You cannot have a large onboard charger because of the space constraint. You can have otherwise everybody would put a very big charger. But in a space constraint is there in automotive and aerospace. Space is the very important there, right? Space size and weight as well. So you can have a small onboard charger. That's why onboard charger takes longer time, 3 hours, 5 hours, 6 hours, sometimes 8 hours to charge the battery. But if you want to charge the battery faster, then you can put the charger outside, a large charger, and take the DC output of the charger directly and charge the battery. That is called the fast charging. You can see the last one. Okay, so this is the DC charge. Okay, DC fast charging. Okay, so this is the HVAC and other things are fairly straight ones. Okay, go to the next one. Now, the different types of motors. Okay, today available in EVs. Okay, you know that the hub motor is used in the smaller vehicles. Okay. So hub motor is nothing but motor is directly put into the wheel. Okay, directly put into the wheel. And when the motor rotates, the wheel rotates and it drives the vehicle. Fairly simple. Okay. Now we can ask that why it is not same technique cannot be used for the larger vehicles, cars, as well as buses and other things. You know, once it is put in the vehicle, it is very simple. So why it is not? Okay. So those who are from electrical background, they understand this one, that the ratio, okay, they are all three are interlinked: power, torque, speed, RPM of the motor. All are three are interlinked. Okay, so power is equal to torque into speed. Okay, so that's what size of the motor. Size of the motor is defined by what? Speed, power, or torque? Speed. Who's called speed? Okay, very good. Okay. Size of the motor. Power. How many power? Let us see. Power. Okay. Power. Okay. How many torque? No one. 1, 2. Excellent. और सिंपली से हाथ उठा के देख लेंगे क्या होता है. Okay. So no problem. Okay. Size of the motor is governed by torque, not by the power. Okay. So higher the torque, okay, higher the size of the motor. Okay. Okay. So what it shows is that, okay, as you reduce for the same power, consider a 4 kilowatt motor is there, and if it is running at 200 RPM, it will produce a larger torque. If the same motor is running at 1000 RPM, it will produce a lesser torque. So same 4 kilowatt motor, if I am designing for 1000 RPM, its size is small. If I am designing for 200 RPM, its size is big. Okay. When I am connecting this motor into a wheel, Okay, compared to motor RPM, wheel RPMs are slow. Okay, even if you are running at 60 kmph, their RPMs are slower than the 3000 or 6000 RPM, which normally my motor runs. So these are slow. When RPMs are slow, naturally the size of the motor goes up and they produce larger torque. Okay, so that's why you can see that one, that first hub motor, you can see that one, it is producing 110 Newton meter, but their RPM is only 350 RPM, very low RPM, slow. Okay, because we need a slow there, and that's why it produces. But whereas the second motor, three-wheeler motor, which is a mid-mount motor, where I am putting a belt and transmission, so that motor can run up to 6000 RPM. But you see the torque. Torque is drastically reduced to 25 to 40 Newton meter. So once the torque is reduced, size of the motor reduces. Okay, and that is the biggest advantage we have in EV. Okay, because in EV, already I mentioned that the size, weight, and those dimensions play an important role. So that's what, okay, design a motor for high power, but operate at a high speed. And at high speed, you reduce the torque, okay, very low torque, the size of the motor comes down drastically. Okay, and but you need a higher torque at the wheel. What you do? You put a transmission. Okay, so consider 1:10 ratio transmission I put, then 10 times higher torque I get. I'm using a smaller motor, low size motor, putting a transmission, just a transmission. Okay, gear ratio, I'll get that one. Okay, that's why these high speed motors, they have a lower torque, okay, higher power, but we have to use a transmission. But in buses, again, bus motor, you can see here, bus motor. In buses, there is no space constraint. Okay, there is no size constraint also. So there you can use again a high torque, low speed motor. Okay, fine. Okay, hope I'm conveying some message. Not sure. Okay, well, at least the torque power difference is come. Okay, so fine. Okay. Okay, next. There is a myth. There was a myth. Now people are understanding that EVs are soft vehicles and they don't produce the torque well, and and their performance is weak. No, it is not at all. Okay, so that is totally wrong. Now you people know it, that EVs performances are much better. Okay, particularly in low speeds, their performance is much better. Their efficiencies are better. Their torques are better. Gradability is better. Everything is better. Okay, so why that is better? Just want to clarify, as students should be knowing this one. So this is a standard curve. Those who come from electrical background, this is a standard curve of a voltage source inverter fed motor, whether it is a PMSM or an induction motor. This is the standard curve. First one is a constant torque, then next is a constant power. Okay, or it is called flux weakling. Okay, so that's why, okay, up to base speed, you are having a constant torque, very high torque and constant. But unlike ICE engine, it is like a, okay, it is a U kind of a thing. Okay, so starting very low, high speed also low, in between there is a good torque. But in ICE vehicles, you are having a very good torque at the beginning, and then the torque is reducing at the high speed. So that's why in high speed, the struggle is there in the EVs compared to ICE vehicles. But in the ICE vehicles, they manage this one by using the different gears. They shift the to the low speed and high speed by using gears. Okay. So let us understand the charging. Okay. So how many of you think that charging is critical in EV? Okay. Thank you. Okay. Thank you. Because EV's charging is very, very critical, because that is the fuel. Okay. So battery is fixed. Battery is like a fuel tank, and you have to fill that one. Okay. Whenever you use it, becomes empty, again you have to fill. So you need to have a charging, either do fast charging or slow charging, but you need to have a charging. Okay. So EVSE stands for Electric Vehicle Supply Equipment. Okay. So EVSE stands for Electric Vehicle Supply Equipment. Anything. Okay. A plug. Okay. A 5 ampere plug is a EVSE, 15 ampere plug is a EVSE, or a type 2 plug which is having all this leakage current protection, over voltage, under voltage, all those protection, that is also EVSE. A fast charger which can provide directly power to the battery is also EVSE. Everything is which providing and power to the electric vehicle is called EVSE. Very simple. Okay. So then there is a, okay, this is a standard one, you know, it power generation from different sources, power is generated, and there is a grid management. Then there is a EVSE management. Particularly in the developed countries, you have to book the charging station, whether it is a AC charging point or it is a DC charging. So you have to book that one and then go there and charge. So this is the overall framework of a charging. Okay, go to the next one. So AC charging, there are standards available right now. Okay, so there is single phase charging, okay, which is what I mentioned, 5 ampere, 10 ampere, 15, okay, whatever the 15 ampere or industrial plug. Then there is a type 2. Type 2 is a global standard AC charging. Okay. So those who are from EV, okay, you people must be knowing what is a type 2 charging. Okay. What is there in the type 2? Can you tell what are those control signals? Anyone? Pilot? Okay, PP and CP. Okay, control pilot and proximity pilot. Okay, so those two signals will make the grid point and the vehicle. Okay, they connect them in a fail-safe way. Okay, so they make their, okay, first they check whether the grounding is, okay, become common. Then once it is done, then they, okay, then they, with the proximity pilot and the control pilot, both sides with the, okay, it is basically a resistor-based analog circuit. So with that, it will connect, and that is a fail-safe connection is done. After that, the power is given to the vehicle. Okay, fail-safe operation. Okay. Similarly, the type 2 3-phase is also available. Okay. Go to the next one. Unlike in AC, in DC, there is no single standard emerged in the market because Japanese brought their vehicles faster, like Nissan Leaf came. Then Chinese have dominated their own, and Europeans and Western countries want to have their own. And India also, we are having our own, but okay. So GBT is from China, Chademo is from Japan, okay, and type 2 combo is from European and Western countries. And India, we are having our own protocol, what is called PC002, and this is called BCP, Bharat Charge Protocol. Okay, fine. Next. Yeah, slowly, okay, let us understand a bit about battery system, because battery cost of in a vehicle, battery cost around 50 to 60% of the total vehicle cost. That is a major one. Slowly it is reducing, drastically it is reducing rather. Nowadays it is coming to around 40%, 40 to 50%, but earlier it was nearly 60%. Okay, so but still it is a dominant one. Let us understand a bit. Okay, go to the next one. Okay, this is an important slide just for informative kind of a thing. What is the range of battery capacities we use in different vehicles in India? It is India specific. In two-wheelers, approximately around 3 kilowatt hour. Okay, kilowatt hour, 3 kilowatt hour battery we use. Okay, in a three-wheeler, around 3 to 7 kilowatt hour. And quadricycles, you know that one, they use for carrying goods and other things, around 3 to 10 kilowatt hour. Okay, so then four-wheelers are on 10 to 20 kilowatt hour, and larger ones use 40 to 60. And buses, all those larger buses, they use around 80 to 150 kilowatt hour. Kilowatt hour is a unit of energy, unit of that is used for the battery capacity. Okay. So this is a very good slide. Okay, if you are having some interest in understanding the battery. Okay. So it is having all the batteries, popular batteries like NMC. Okay. Then we are having LFP, which is these two are very popularly used in India. Everyone knows, okay, that these two batteries. Then there is a LTO, okay, which is coming up well and which is suitable for an environment like India. Okay. Then there is a LCO and NCA as well. NCA is being used in Tesla and others. Okay. So what this slide provides is what is their base voltage. Base voltage is nothing but a steady state voltage of once this battery is fully charged. And okay, what is the steady its voltage? That is very critical. The higher the voltage, okay, then the higher is the capacity because the current is same. Consider if it is 30H NMC, 30H LFP, because LFP you see here 3.2 volts, NMC you see here 3.65 or 3.7. So that much higher, it will be having higher capacity. Okay, because basically power is nothing but voltage into current. AH is nothing but its ampere hour capacity. So AH into the voltage provides the energy. Okay, so higher the voltage, if the same AH is there, then that cell is having higher density, higher capacity. Okay. So next one is the energy density. Energy density is very critical again because in the same space, giving the higher energy, okay, it will be having higher energy. Okay, lower energy density is nothing but we require larger space. So we have to look for higher energy density. Okay, cells. So LFP, if you take, it is 80 to 120. Nowadays, it is coming up to 150 Ah, 150 watt hour per kg. But NMC is better. Okay, it is more than 200 okay, watt hour per kg. Okay. We have to see the other aspect is temperature. Even the higher energy density, because these cells have been developed by the countries where the temperatures are normally less than 35 degrees. Okay, even northern China, okay, where most of the EV densities are there. And also the European countries, their temperatures very rarely go beyond 35. But in India, most of our cities, temperature will be beyond 35 degrees. Sometimes it goes to 45 or sometimes it reaches 50 degrees as well. So for Indian operations, we have to consider the temperature as one of the critical parameter. Okay, so NMC is struggling in India. Okay, it is being used well, but okay, there are some problems there. LFP is looking to be safe. It is operating up to 55 degrees. Okay, but we have to consider this aspect critically when we are taking the battery. Of course, the next one is the safety aspects. Okay, whether these cells are safe or not. Okay. Okay, then next one. So battery management system, I will not go, okay. How many of you are interested in BMS? And so unlike the lead acid battery, the lithium ion batteries by nature, they are unstable. Okay. Lead acid batteries, when you charge, once they are fully charged, automatically they will stop drawing the current. Okay, so once they are fully charged, automatically the current will come down, which is going inside. It will stop. So considering that one, so okay, even if you keep it charging for long, nothing will happen. It will not draw the current. Whereas the lithium-ion batteries, both NMC and LFPs and all this, when they become unstable when they are fully charged, and they become unstable when they are fully discharged as well. Okay. So when you are charging, you have to take care that when this is fully charged, you have to immediately notice that it is fully charged and stop the charging. Otherwise, it will go to instability. It may burst. Okay. And when you are driving, when it is fully discharged, you have to notice that one and stop. Okay, drawing current from the battery. Otherwise, the whole cell may damage. Okay, so it may degrade itself. You may not use it again. So that's what a lithium-ion battery requires an intelligent electronics to be associated with the battery, which continuously monitors the voltage continuously monitors the temperature and current as well to see that we are operating in the safe zone. Whenever we go to the unsafe zone, we have to stop the charging as well as discharging. That is the BMS. And okay, for that one, this circuit is shown here for monitoring. So other one is a cell balancing. Okay. So last bench two guys. Okay, if you are not interested, you can move. Those two guys, yellow shirt and the right, okay, and adjacent to yellow. Please leave, no problem. Please leave. White shirt and yellow shirt. You both guys can leave. We are from industry, not from academia, that we can, okay, we can take all these things. Okay, so we are from industry. Okay, no problem. We'll continue. Okay, cell balancing is one of the most critical okay thing. Okay, what is cell balancing? Batteries, you know that it is a 3.2 volts battery. Okay, but 3.2 volts is okay, useless battery. Nowhere, nobody uses. You have to bring to 12 volts at 24 volts. Normally in EVs, we use 48 volts, sometimes 72, sometimes 96. Okay, and nowadays we are going for 320, 400 volts. Okay, so when you connect to increase this voltage, you have to connect them in series. Okay, so once you connect these cells, okay, consider 16 cells you have to connect to get a 48 volts. Okay, so to get a 320 volts, you have to connect 100 cells in series. Once you connect all these cells in series, okay, so if one of these cell is defective, like I noticed one or two people, okay, so then it disturbs the whole. Okay, because they are connected in series, they are not isolated from the system. Okay, so because current has to pass through all these cells. Okay, if one cell is weak, then that cell charges faster. Okay, I'm having 16 cells. Please understand this one. This is a very critical one. Okay, those who are interested in the EVs. In 16 cells are connected in series. If one cell is weak, because it is weak, it charges faster. And once it charges faster, because your BMS is continuously monitoring, it has fully charged, then it stops charging. Because it stops charging others as well. All others have not charged. So what is effective? Effectively, it is whole energy available is very less. Okay. Now during discharging, what happens? During discharging also, this weak cell discharges faster. Okay, and it has reached the unstable state. BMS is monitoring. Oh, it shows that it has reached the unstable state. Stop it. So still energy is available in other cells. You are neither fully charging, neither fully discharging. Okay, effectively you are not utilizing the capacity. Because of this, your range reduces. If your normal range is considered 100 kilometers, with this unbalancing, you may get around 50, 60, sometimes 70 kilometers. You will not get a complete 100. That's what the cell balancing. Whenever you go to any battery company, this one, cell balancing is very critical. Every day they will be talking about cell balancing. So cell balancing is nothing but you have to, once this charging is done, you have to see that that is fully charged one. You have to bring it down to the average charging. Okay, so that all are in this one. Then again charge them so that they absorb larger energy. Okay, and during discharging also they will discharge well. So that is the cell balancing. Okay, cell balancing is very critical in a battery system. Go to the next one. SOC and SOH. Okay, You may be knowing long form. What is SOC? State of charge. SOH? State of health. Okay, state of charge is nothing but when I charge the battery, how much is energy available there. Okay, so if cell balancing is not proper, okay, still it shows the SOC of 100%, the energy available is less. Okay, so when it is fully charged, it is called SOC, state of charge. State of health is nothing but the degradation of the battery, the health of the battery. Okay, so I mentioned that out of 16, one cell is weak. So that is identified by state of the health. Okay, so if I'm not getting a complete 100% energy, then definitely there is some weak cell in this cycle. So that I have to identify. That is using the SOH algorithm I have to do. Okay, fine. Next. Okay, so how the cell balancing is done. Okay, so there are two types of BMS available today in the market. One is centralized BMS. When cells are small, up to 31 cells, you can use a single processor, single board, wherein all the voltages you can monitor from the single board. Okay, temperatures also you can monitor. Okay, and also current can be taken to single board because only up to 31 cells, they are closely located. All those 31 wires can be pulled to this one. But once you become 100 cells and they are very large batteries and other things, pulling those cables and other things becomes nuisance. It becomes sometimes not reliable as well. So in such a system, go to the next one, we need to have a distributed one. So you can have a master, one master controller. Then there is slaves attached to 12 cells or 14 cells or sometimes 10 cells based on your design. Majority of the time people use around 12 cells as a standard one. Each 12 cells, you have a slave which collects all the voltage and the temperatures from 12 cells slave. And like this, you can have multiple slaves. And from slave to master, you will be having only the communication through CAN communication or whatever the serial communication you are using. Just two cables will go. So now cables will be reduced, okay, coming to the master. Okay. Okay, then. So this is a business slide rather. Okay, try to understand. Okay, so what is happening here? In 2010, if you see, the batteries available will be around 80 watt-hours per kg. Density was very, very low. And today you see 400 watt-hour per kg. So in the same space, I can have 5 times higher capacity in the same space. Earlier, consider if I was getting around 100 kilometers range, today I can get 500 kilometers range in the same speed, same space, same vehicle. Okay. Next. Yeah, that's what, okay, this slide shows. Okay, go to the next one. So this is the other important, this one. So cost of these batteries are declining drastically. Okay. So parity has come already. Okay. So, like solar, so okay, solar power parity has come with the grid power. Okay. Rather solar power is now cheaper than the grid power. Okay. Similar one, okay, in this one also parity is very soon it is coming. Okay, earlier it was around 750 to 800 USD per kilowatt hour. Okay, 1 kilowatt hour was costing around 750 to $800. Now it is around $100. It has drastically reduced. It is okay. Further, I'm not sure whether it will reduce because there are some China is further increasing and other things, and okay, because it is suddenly there is a big demand for the batteries. Okay, so because of that, cost is not further reducing. Okay, go to the next one. Okay, I'll briefly touch upon challenges. Okay, so if you are interested, go back. Okay. How many are interested? Otherwise, we will wind up here. Okay, interested. Okay, fine. Okay. Go to the challenges. Okay. So this is okay. No politics in this one. Just okay. Or even UK Prime Minister is an Indian now, so there is nothing wrong in showing a UK now. Okay, so just for comparison, I have taken the EVSEs. EVSE, you know it. EVSE is basically electric vehicle supply equipment points. This is public EVSEs available for public. So in UK and in India. Okay. So India is a very large country. Okay. UK is very small. Okay. Much smaller country. Okay. I don't know. Okay. UP is much bigger, maybe. Okay. It is like a Karnataka kind of a very small state. Okay. So you geographically, but they are having large numbers compared to overall India. Okay. So we, okay. Indian philosophy is a bit different one. Once we start doing, we do very fast. But okay, right now this is the state. But so if you see the right side slide, there is a big information is here for young people like you. Big message. That's why, okay, you see if in 2015, there are only 1,62,000 AC charge points. And by 2020, they have become 20 lakhs. And they will be becoming 2 crores. 2 crore charge points by 2030. Okay, that's why you see so many young people, those who are coming out of universities, they are going into charging stations, they are starting charge, okay. The charge points, AC charge point companies, DC charging stations and other things. Because of this one, there is a phenomenal growth, phenomenal, okay. So 10 times from 2020 to 2030. So every year there is a 100% growth is there in this one, okay, in the charging station. And India, nothing is there today. You can see the blank here. So there is a huge opportunity in India. This is a global number, and India it is much more rather, okay, much higher. Okay, so that's why this is, for young people there is a big opportunity. Okay, go to the next one. Okay, so this is a photo from okay, developed countries. Okay, they are having built the infrastructure so well. Okay, so many nice cars are getting charged. Okay, but a similar one, okay, we need to have. Okay, so in India, this is okay. This is a challenge, and this okay. So okay, we are working. The government is putting a lot of effort. Okay, even today also, I saw a morning a DST director's message saying there is no problem of what you can say, what he is saying, the installation of EVSEs, but there is a problem of availability of the power to those okay, EVSEs. Okay, so it is work is being done. Okay, so okay, let us wait for some more time, and it will be happening. Okay, so go to the next one. Let us understand more on the technical points. Okay, rather than putting more effort on the infrastructure, there is infrastructure people are there, they are working. So new technology creating new challenges. Okay, so what are those challenges? These are for the engineers to solve, for us to solve. Okay, so functional safety. So I'll ask later, okay, on the functional safety. Let's first touch upon these points. Independent systems. There are multiple systems, okay. So there is a low voltage system, there is a high voltage system, there is a mechanical system, there is a body system, there is a EV powertrain system. There are multiple independent systems, multiple voltages. There is a high voltage 48 volts, 96 volt system. Then for all these auxiliaries, you are having a 12 volt system. So, okay. Then because you have to put the battery to get the range. Okay, so it is increasing the weight compared to the ICE vehicle for the same range. Okay, increasing the weight. And virtual verification. Okay, already professor told in the morning that okay, today we can have a virtual verification. Okay, we can see a Boeing engine being opened in somewhere in the France, and sitting here we can see that one. So those kind of things are happening, and your vehicle also will be having virtual verification is needed. It is being done. And packaging is a constant, huge packaging, because you have to put battery, you have to put so many things, drivetrain, motor, and other things. There are some slides, I'll show them. Functional safety. What is the definition of functional safety? Basic definition. Anyone? Whatever you think. Oh, fine. Excellent. Anything? Okay, basic definition of safety. Okay, please remember these things. Okay, I also learned like this attending some okay fellows lectures. Okay, basic safety is safety has come from European Western background. Okay, their population is less. Okay, even technology is much higher, population is less, and they give highest value to life of a person. Okay, highest weightage. Okay, so safety is nothing but it is primarily attached to safety of a human being. Okay, so fail-safe system is nothing but it should not fail and enter into a hazardous situation to a person. Okay, and because these vehicles are used by the humans, these are designed for the humans. Okay, all the safety aspects need to be addressed. Okay, so that's the functional safety. Okay, so safety is very critical. Okay, and in fail safety design, the aerospace uses 2 out of 2, 2 out of 3 kind of a architecture. That is nothing but for everything they will be having a redundancy of one system. Okay, that is called 2 out of 2. Sometimes they use 3 systems, 2 out of 3. Even in railways also they use 3 is nothing but if you are monitoring the temperature, you monitor with the 3 sensors, and then you check if 2 are matching, then only you clear the signal. That's why. Okay, then you may otherwise you make the red signal. Okay, so that is called 2 out of 3. 2 out of 2 is nothing but minimum 2 sensors I have to use. So that is by doing that one you will have the safety. So why this safety is very critical in electronics? Anyone knows why it has become so critical in electronics? In mechanical systems, we know if it fails in okay. In otherwise, if it fails, we know the failure condition. In electronics, there is a trouble. In electronic system, particularly those you must have studied 8255 PPI, peripheral interface chip. In peripheral interface chips, if output fails, we don't know whether it is going to asserted high or asserted low. When chip fails, it can fail in high or low. If it is failing in low, I know that, whenever it fails, I know the condition that, I can design circuit like that. If it fails in high also, I can design circuit like that. But today I don't know whether it fails in high or low. Because of digital circuit failure, I have to go for the fail safety operations because of these redundancies, 2 out of 2, 2 out of 3, and all these things. Okay, so anyhow, so a very complex topic. Okay, just remember whatever brief ones. Okay, other challenges. So the other one is a standard wiring harness. Now with this EVs and other things, the wiring harness is becoming like this mess. Okay, with so many wires, so many things, and so many. In this one, high voltage is there. In this one, low voltage, 12 volts is there. In this, communication is there, and so many things are there. So everything is a mess. Okay, so it is very complex one. Okay, go to the next one. So this is the real picture of an EV. Okay, over this you will be sitting. Okay. Okay. So okay. So this is okay. The all oranges are high power one, high voltage cables. Okay, and we can see the motors and chargers and other things connected here, batteries. So such a complex work. Okay, so it is E side also it is huge complex. Next one. Then there are many safety requirements. Already I told you. Okay, there are so many things. Okay, from the software point of view, you have to take care. From the hazard point of view, you have to take care. From the hardware point of view, you have to take care. If anywhere one connector is loose or open, then system should stop. Okay, that is the basic requirement. Okay, okay, fine. Next. Yeah, this is my last slide. Okay. So what people are saying. Okay. So we see more challenge in next 5 years than there has been last 50 years because of the EV evolution. Okay. So you are seeing so many new things. Everything is changing very fast. 80% of the product innovation and differentiation now in electrical, electronics and software. Already you know this one. This is from Daimler CI. Okay. And the next one is a Matchtech. Okay. This is basically a recruitment company. Okay. So rise of EV for next 10 years will create a demand for different kind of, basically different kind of skills. Okay, that's what he is saying. Okay, naturally that is happening. And from the Visteon, they say that there has been never been more exciting time to be in automotive. So everything is new challenge, and new things are happening. Okay. So, okay, the further things are there, just we can have a look. Okay. So, yeah, with this one, I'm done. And if any questions are there, I'll be happy to take. Okay. Thank you. Yeah, please.
As the word kind of charges are using in India and it's in industry.
So there are two questions, different questions. What kind of chargers are being used in India, and what are the industries? Okay.
Yes.
So chargers, because India is a very unique situation now, because our 80% of the vehicles on road, only country in the world where 80% of the vehicles on the road are two-wheelers. Okay. Not like Western countries and okay, unlike other countries. So, and those two-wheelers are highly constrained by economics. Okay. Okay. So considering that one, our chargers, majority of chargers today in those two-wheelers, smaller scooties and other things, they are very low power, and they are not onboard chargers. They are portable offboard chargers. Portable offboard, normally you will have a large DC charger. Instead of that one, you are having a portable, same onboard charger, portable one, small. Because in an onboard charger, I need to manage all thermal, everything in that small space, and automotive components. Instead of that one, Indian designs are highly always that some tricky designs will be there, low cost designs. So they are portable chargers, but they are from 250 watt to around 3 kilowatt of the chargers. And there are many companies, many charger companies are there. Okay. So big companies like Delta, ABB, the small companies like Exicoms, there are many companies are there, and many smaller startups are there. Okay, so young people, many companies. Please.
How can we reduce the wiring system? Lots of mess. Is it any way?
Yeah. So how can we reduce the wiring system is the question. Okay, very best question now. Okay, so how can we reduce the wiring system? The two things. One is power cables you cannot reduce because we have to pass the power. Because that is like a mechanical system. No mechanical system we can cut. Similarly, here the electrical system also cannot be cut. So those cables will remain. The other things like BMS and other things, there is a definite low voltage and particularly communication ones. There is a possibility. There is a wireless communication there. There is a wireless BMS already emerged. There are no cables at all. Voltage, everything is monitored there, battery, and from there wirelessly it is communicated to the master. Okay.
Any questions from students?
Can you repeat?
How does weight affect the components of the
How does weight?
Weight affects the components of the
Okay. How does weight influences the performance of a? Oh, it is the what you can say. Weight is the it is a dynamic equation. You know it. You must be already knowing. that weight plays a very, very, very important role. Okay, particularly in the high speed one, weight is having a huge effect. Okay, so weight, there are many parameters along with the weight. Okay, just for that one. Frontal area plays an important role, AF. Weight and mass plays very important role. Okay, then there are what are those here? Okay, what is that? Velocity. Velocity plays some role. Okay, so okay, these are the okay, and tire resistance plays. Gradient resistance plays a gradient, of course, it plays a role. Okay, so these are the things. Okay, they play a role. Weight is critical parameter.
Any other question?
So, sir, one more question I have. What kind of technology we are using for master slave to balance the battery cell?
Question is what kind of technology is being used for the master slave for balancing of the cells in a battery? Okay.
Yes. Yes.
So there are two types of balancing. Okay, so one is active balancing and other is passive balancing. So in the active balancing, you have to use for each cell two switches to okay, charge and discharge them. Okay, and that can happen once the cell is fully okay, when the voltage goes high or when the voltage is low. When the voltage is low, I can charge it more. Once the voltage is high, I can discharge it. Okay, so by using those switches. But in a okay, so that is the one, and in a distributed also it is possible, because each slave can have that one. That what I mentioned, the 12 a slave which can manage the 12 batteries. So 12 balancing register. Okay, this one it can have circuits. Similarly, in a passive also it is same, but passive only difference is I can only discharge. I cannot charge it. Okay. So considering that one, okay, so only the cell which goes to the higher voltage, I can reduce it, okay, and bring to the other averaging it, and then again I can recharge. But in a active, I can charge as well. That is it. But in distributed also it is same. Okay, it is for whatever the 12 cell or 10 cell, the slave, it can have its own balancing circuit. Yeah, it is. Yeah, thank you all. Thanks a lot. Okay.
Now I would like to call our esteemed faculty member, Dr. Ishwar Krishna Musadda sir, for vote of thanks. Over to you, sir.
Thank you, Dhanashri. Good afternoon to one and all gathered here. On this wonderful and special afternoon, I feel privileged to propose a vote of thanks to our esteemed guest here. So, as a part of this fourth expert talk on EV powertrain, which is being organized as a part of Amity Industry Academia Technology Forum by Amity Institute of Technology. On behalf of Amity Institute of Technology, Amity University, Uttar Pradesh, and entire fraternity of Amity University, I extend a really heartfelt thanks to our esteemed guest here, Dr. Naikodi, CTO, JLN Phoenix Energy, for nicely articulating your presentation and sharing his valuable thoughts with every one of us, and also posing some kind of interesting questions in between his presentation. I really listed many points to discuss, but due to short of time, I'm not touching upon all that because he has given enormous amount of knowledge in this very less time. Okay, and thanks once again, sir. And of course, experience speaks. I hope you guys realize that fact today, right? And I also thank Mr. Tanmay and Ms. Kavita from JLN Phoenix Energy for your gracious presence. And the benchmark that the Amity University has set, not only just in India, but also globally, designing and developing an unparalleled education system would not have been possible without the tireless efforts and visionary thoughts of our Honorable Founder President, Dr. Ashok Kumar Chauhan, and our Honorable Chancellor, Dr. Atul Chauhan. It's the seeds of the knowledge and wisdom that has allowed us to grow and propel in our careers. A special mention to our most respected and charismatic Vice Chancellor, Madam Dr. Balvinder Shukla, for being the catalyst and that stimulated us to do our best and standing a pillars of the strength. With a deep sense of appreciation, I thank Professor Vivek Kumar, HY Amity Institute of Technology, for his untiringly efforts for making this event very successful one. I'm also thankful to all the participants for your patience, listening, and active participation. I'm also thankful to our team of dedicated students and faculty colleagues, okay, without whom this event would not be possible. I also especially thank our IT team present online for doing all the necessary arrangements for hosting the program. Thanks, IT team. So, with your permission, sir, we'll close the event. Thanks once again for your gracious presence. Thank you. IT team, we can end the session.